Do you ever hear those commercials for some pharmaceutical drug where it says something like, talk to your doctor before taking if you have a G6PD deficiency? And you're like, I don't even know what a G6PD deficiency is, let alone if I have one. And well, if I do have one and it's something I should be concerned about, isn't it something my doctor should be telling me? Well, your doctor might actually not know because despite G6PD deficiency being the most common genetic metabolic disorder, it's actually not routinely screened for because typically it doesn't cause much of a problem. But it can cause problems if patients take certain medications or have various stressors. And so, why is this? Well, it has to do with, well, what's G6PD? G6PD is kind of one of the most important enzymes in the pentose phosphate pathway. So now, what's the pentose phosphate pathway? Well, I'm glad you asked, because that's the subject of today's lesson. We're going to talk about the pentose phosphate pathway. Well, and we'll see why G6PD deficiency can be a problem. This is how that comes about is basically the pentose phosphate pathway has two main purposes. One purpose is to make NADPH, and one purpose is to make ribose and other things that you can make like ribose. So DNA and RNA, various cofactors, that's kind of one part of the pentose phosphate pathway. And the other part is getting this NADPH. And it's the NADPH that comes into play when we talk about our G6PD deficiency. Don't confuse NADPH and NADH. So they do similar things in that both are able to pass along electrons. And so they're both able to give and take electrons in the form of hydrides. But as we talked about with NAD+, well, that we want to keep mostly for our oxidative reactions. So our reactions in which we're doing like catabolism. So we saw in glycolysis, we're using NAD+, and we were reducing it to NADH, which then we could take through to like this electron transport chain to cash in to make ATP. We saw that if we wanted to keep glycolysis going, we would then have to regenerate the NAD+, either through the electron transport chain or through fermentation. So remember, we went to lactate if we needed to regenerate that NAD+ anaerobically. And we did that so that we could keep a high ratio of NAD+ to NADH so that we could use it for oxidative reactions. Similarly, but conversely, we want to keep NADPH at a higher ratio than NADP+ so that we could use it for anabolic reactions. We want to be able to use NADPH to reduce things. One of the things that we're going to want to reduce are going to be reactive oxygen species. So our ROS, these are things like oxygen-free radicals, superoxides, various high-energy oxygen molecules that can react with like your RNA, your DNA, your proteins, your lipids, and cause damage. So our cells have these like antioxidant systems. They stock up on things like GSH, which can basically take the hit from the oxidation. So they get oxidized instead of your DNA and your proteins and your RNA getting oxidized. We'll talk a little bit more about this. But bottom line is that in order to regenerate those antioxidants to do things again, similarly, like we needed to regenerate the NAD+ for glycolysis, we're going to need to regenerate the NADPH if we want to use it to regenerate our antioxidants, or if we want to use it for anabolic reactions. So remember, our NADH and our NAD+ was going to be used for catabolic reactions, and our NADPH is going to be used for anabolic reactions. We'll talk later in the semester about how some of these reactions are things like making lipids. Other things you can make are like steroids, various like proline making needs it, as well as some other things like making your DNA from your RNA and various other reasons why we need the NADPH, and we can get the NADPH from our pentose phosphate pathway. More specifically, we're getting it from this kind of oxidative phase of the pentose phosphate pathway. So we talk about these kind of like, we can split the pentose phosphate pathway into two phases. We can talk about an oxidative phase in which we generate NADPH, and we can talk about a non-oxidative phase in which we can take the carbons that are left over after the oxidative phase and kind of scramble them around and keep and keep putting them into the pathway if we want a bunch of NADPH. Or we could take those carbons and we can actually use the ribose, convert it to ribose, the ribulose 5-phosphate we get from the oxidative phase into ribose 5-phosphate, which we can then use to make nucleotides and DNA and stuff like this. So we'll see that there's a variety of different pathways that we'll take the pentose phosphate pathway. And one of the key things we'll talk about is, well, how do you decide what you want to do? So the pathway is going to be regulated by your need. Like, do you need a bunch of NADPH? Do you need a bunch of ribose? If you need a bunch of ribose, you'll go that non-oxidative way. And if you want a bunch of NADPH, you're going to go the oxidative way. So those are kind of like the key things for the pentose phosphate pathway, is that we can generate the ribose and we can generate the NADPH. The rest is just logistics of how we're going to go about that. Step back and look at where we're starting. So we're basically taking the pentose phosphate pathway is kind of like an alternative route that we could take from that glucose that we took in. So the glucose enters the body, or I mean, it enters the cell and it gets trapped. It gets trapped by our hexokinase step. Hexokinase phosphorylates the 6th position. Now you've got your glucose 6-phosphate, and what are you going to do with it? We talked about a variety of different things that we could do with the glucose. We talked about glycolysis, in which we took the glucose and we broke it down into pyruvate. And we talked about how we can actually make glucose from pyruvate through gluconeogenesis. In those cases, in the case of glycolysis, we take that glucose 6-phosphate, we use phosphoglucose isomerase to give us fructose 6-phosphate, which then we can take through this glycolysis pathway. In the case of what if we want to store the glucose, we can use phosphoglucomutase to give us glucose 1-phosphate, which we could then store as glycogen. Now we're going to look at this left-hand side of things, where we talk about this pentose phosphate pathway. Here, our first step is going to be glucose 6-phosphate dehydrogenase. Yep, that's our G6PD. We can see that it's going to take our glucose 6-phosphate and it's going to oxidize it to give us 6-phosphogluconolactone. So again, we want to keep NADPH in its reduced form so that we can use it for other things. So our pentose phosphate pathway, you can think of it kind of like the role of fermentation and regenerating NAD+, but here we're using it to generate NADPH. The NADPH we can then use to combat reactive oxygen species, so we can regenerate our antioxidants, and we can use it to do anabolic reactions like lipid synthesis. You'll see that when we went from glucose 6-phosphate to fructose 6-phosphate in glycolysis, or from glucose 6-phosphate to glucose 1-phosphate in glycogenesis, those are reversible reactions. But when we use G6PD, basically here, this is going to be an irreversible reaction where we're generating 6-phosphogluconolactone, and then we have gluconatase, which is basically going to break that open to give us 6-phosphogluconate. We'll look at this in a second. But then we generate a second NADPH in the 6-phosphogluconate dehydrogenase step. So we're generating 2 NADPHs. And we're going to also, in this step, we're going to be losing the CO2. So we're going from a 6-carbon sugar to a 5-carbon sugar. More specifically, we're ending up with this ribulose 5-phosphate. All these arrows were single-headed, these were irreversible reactions. And this constitutes what we call the oxidative phase of the pentose phosphate pathway. Then we can take that ribulose 5-phosphate. We can use an isomerase or an epimerase. Basically, we can scramble things up to give us ribose 5-phosphate or xylulose 5-phosphate. And the ribose 5-phosphate, we can go and we can use it and we can make nucleotides, we can make DNA, RNA, coenzymes. Or what we could do is we could funnel it back. We can combine it with other carbons in order to basically regenerate this glucose 6-phosphate that we could take back through the pathway if we want to go the oxidative phase. Or what we could do is we could basically regenerate the glucose. We could feed these products into the glycolytic pathway and take them down if we want to go make energy. So we'll see that we can go a bunch of different pathways, and we can actually go from glycolysis. So these are all double-headed arrows. We'll see that these are carried out by like transaldolase and transketolase enzymes. Basically, what they're doing is they're just shifting carbons around from one sugar to another sugar, either 2 at a time in the case of our transketolase, or 3 at a time in our case of our transaldolase. And so they're just moving things around. And they're going to give us 2 things that we can put into the glycolysis and 2 things that we can take out of glycolysis: fructose 6-phosphate and glyceraldehyde 3-phosphate. These can both come in and out of glycolysis and the pentose phosphate pathway. And through transaldolase and transketolase, we're able to interconvert them. We'll talk about how this happens a little, but we're not going to focus on the details of it because, well, it's kind of brain scrambling. Let's step back and look at kind of the simpler part of it, the oxidative phase. So remember, this is the irreversible part where you're producing this NADPH. This is happening up here from this glucose 6-phosphate. So it's before this fructose 6-phosphate to fructose 1,6-bisphosphate, this phosphofructokinase step. Remember, we said that this step was going to be the committed step of glycolysis. So when you have glucose 6-phosphate, you can go all these different ways. But once you got fructose 6-phosphate, well, now if you use PFK1, you're basically going to be committing yourself to this glycolysis fate. And so this would then be, or at least the fate, you could still go and put it back into the pentose phosphate pathway. But at this point, you're putting things into and out of the pentose phosphate pathway after the irreversible part, after this oxidative phase. So stepping back and looking at this oxidative phase where we're generating our NADPH. We're going to generate 2 NADPH, and we're going to lose a CO2. The first step is also the first step where we generate the NADPH, and this is going to be our glucose 6-phosphate dehydrogenase step. So you might see a G6PD, you might see a G6PDH, either of those. Basically, what it's going to do is it's going to oxidize glucose 6-phosphate to 6-phosphogluconolactone. You can see that we went from an alcohol to a ketone. And in this case, we're generating 1 NADPH. In the next step, we go from 6-phosphogluconolactone to 6-phosphogluconate. And this is basically, you're just hydrolyzing this open. This can actually happen non-enzymatically, but because this is really unstable, but this enzyme, the 6-phosphogluconolactonase, is going to help with that. But this is going to be highly favorable, and so this is going to help drive this forward and make the combination of these incredibly, basically irreversible. What's going to happen to the 6-phosphogluconate if we look? So basically, I'm just moving this from up here to down here. What's going to happen here is now you're going to be generating another NADPH, and this is where you're losing the CO2. So you can see that we're going from this 6-carbon compound to this 5-carbon compound, and then that is the end of our oxidative phase. And from here on out, we have these reversible steps. So we can go from that ribose 5-phosphate that we generated from the oxidative phase, and we can kind of swap things around to give us our ribose 5-phosphate, which then we can either use to make RNA and nucleotides and all that good stuff, or we can do other things with it. So that was the oxidative phase. We produced 2 NADPH, and we need it to combat our oxidative stress and for our lipid and steroid synthesis. So we'll talk more about the lipid and steroid synthesis later in the semester. In terms of our oxidative stress, I'd like you to know about the glutathione. So we have glutathione reductase is actually going to be using the NADPH to regenerate glutathione. And so glutathione is kind of like one of our cell's main antioxidants. You can see it's kind of built from amino acids, including cysteines. And just like we saw, cysteines can form crosslinks between proteins. Cysteines can form crosslinks between glutathiones. Remember that this is going to be an oxidation reaction. These sulfurs are going from being bound to a hydrogen, which they kind of get the electron, to being bound to a sulfur in which they have to share electrons. This is going to be oxidized. This is reduced. How do you go from reduced to oxidized? Well, you basically, reactive oxygen species kind of react with you. And so the reactive oxygen species, they react with the glutathiones, and the glutathiones then become oxidized. This is helpful for your cells because it's preventing those reactive oxygen species from interacting with other molecules. But in order to regenerate the glutathione, well, now you're going to need to reduce it. And the main reducing agent we keep in our cells is going to be this NADPH. The NADPH can then go and it can reduce the oxidized glutathione to give us glutathione that can now be an antioxidant again. So this is happening with the help of this glutathione reductase. There are also like thioredoxin reductase that uses NADPH, various other kind of antioxidant roles that we need the NADPH for. In the case of G6PD deficiency, well, if you can't make enough NADPH, your cells can't keep up with the stress. This is most important in your red blood cells, because in your red blood cells, well, what's going on in there? What's going on in there is a couple things. One is that you're carrying a bunch of oxygen. When you hear oxygen, think oxidative reactive oxygen species. So there's a lot of opportunity for this reactive oxygen species to develop. In addition, there's not kind of alternative routes for NADPH generation in your red blood cells. So in your other cells, you have other ways to make NADPH. You have things like glycerol 3-phosphate dehydrogenase. You have things like malic enzyme, various ways in which you can make NADPH that you don't have in your red blood cells. And so those red blood cells are going to be more vulnerable. In the case of people who have this G6PD deficiency, well, they're not able to regenerate NADPH fast enough to keep up with the oxidative stress. This can cause the cells to get destroyed and in a condition called hemolytic anemia. So anemia, lack of blood cells, hemolytic, basically the cells are lysing or breaking, and that can be caused by this G6PD deficiency that we'll return to at the end. So going back, we ended up with our oxidative phase. At their oxidative phase, we're with this ribose 5-phosphate is going to be where we're left. Now, what do we want to do with the ribose 5-phosphate? Well, one of the things that we could do is just take it to make ribose 5-phosphate. So we just isomerize this ribose 5-phosphate. We basically take it from a ketose to an aldose, and then we could use that to make RNA and things. But what if we don't need those RNA? What if we don't need DNA? What if instead we need more NADPH? Or what if instead we just want energy? You can imagine that we're not going to get as much energy from this as we would from glycolysis because, well, we've already kind of taken a CO2 away and we didn't generate any energy. But we said that we could enter the glycolytic pathway. And so there still is a chance for us to go down and make more energy. We could basically, if we take those carbons, we could scramble them around to give us fructose 6-phosphate and glyceraldehyde 3-phosphate. Basically, these are going to be 5 carbons. You can, on net, you can basically take 6 of those 5 carbon compounds and make 5 6-carbon compounds. So you can make glucose 6-phosphate that you could put through, or basically, instead of making the glucose 6-phosphate, you can just take these products directly in here, so your glyceraldehyde 3-phosphate and your fructose 6-phosphate, and take them down the pathway. The same net result, and so if you think about having 5 6 carbons, now basically you would then be generating the ATP from a glucose 6-phosphate, the amount of ATP you would get from 5 glucose 6-phosphates, instead of the amount of ATP you would get if you started with 6 glucose 6-phosphates. Because you lost the CO2 here, but you didn't generate any ATP, but you did generate these 2 NADPH that are really valuable. So if you really, really wanted energy and you didn't want the NADPH, you wouldn't go through the pentose phosphate pathway. And we'll talk about how like this pathway can be regulated. Like when do you go this way versus just go from that glucose 6-phosphate into glycolysis. And that largely has to do with whether or not you need NADPH. But if you do need NADPH and then you want energy and you don't want the ribose, now you can feed back into the pentose phosphate, into the glycolysis pathway and go down and again, get energy that way. Or you could use it to regenerate the glucose 6-phosphates if you did want just the NADPH. So we'll go more into how the regulation happens. But let's just talk a little bit about the details. The details really scramble your head, and so I don't want you to worry about all of the carbon scrambling details. We'll go do an exercise in class to kind of see what's happening, but basically you're just moving carbon units over. They're happening through these 2 enzymes. I'd like you to know the names of these enzymes, these transaldolase and this transketolase. they're going to be, both of them, regardless of their name, they're both going to be taking carbons from a ketose and putting them on an aldose. This is going to give you a longer ketose and a shorter aldose. In a trans-aldolase reaction, you're moving 3 carbons at a time, and in a trans-ketolase reaction, you're moving 2 carbons at a time. The way that I remember this is that basically a trans-aldolase, if we think back, we saw an aldolase in our glycolysis reaction, this fructose bisphosphate aldolase, which typically we just call aldolase. And basically what it did was it took the 6-carbon glucose, 6-carbon fructose 1,6-bisphosphate, so the 6-carbon sugar, and it split it into 2 3-carbon sugars. So we're basically, if you think about it kind of in reverse, we would be putting a 3-carbon sugar on a 3-carbon sugar to give us a 6-carbon sugar. We're transferring these 3-carbon units. Similarly, transaldolase is going to transfer 3-carbon units. So they have it colored here. You can kind of see if we look at one of these transaldolase steps. So here we're taking septuhydrolose 7-phosphate and glyceraldehyde 3-phosphate, and we're taking these top 3 carbons from this cedoheptulose 7-phosphate and sticking them on the glyceraldehyde 3-phosphate. And so in this process, we're basically making a longer ketone and we're making a shorter aldose. And so we transferred this 3 carbons over on top of here. Now this is a ketose and this is an aldose. And this erythrose 4-phosphate, it can now feed into this and it can react with xylulose 5-phosphate to give us fructose 6-phosphate and glyceraldehyde 6-phosphate, which you might remember are products of our glycolysis path, or intermediates of our glycolysis pathway. So we got our fructose 6-phosphate and we got our glyceraldehyde 3-phosphate. So these can directly come in and out of glycolysis. In order to do that second reaction, though, we needed to use the transketolase. The transketolase is going to transfer 2 carbons. I remember this because the K in transketolase has kind of like 2 arms. So what it's doing is it's going to be transferring 2 carbons at a time. In this case, it's transferring the 2 carbons for this top 2 carbons from xylulose 5-phosphate onto our erythrose 4-phosphate, giving us fructose 6-phosphate and leaving the remainder of this as glyceraldehyde 3-phosphate. So there are basically a couple of transketolase reactions where so you have that one that we just looked at, and then you also have xylulose 5-phosphate plus ribose 5-phosphate gives you glyceraldehyde 3-phosphate and acetoheptulase 7-phosphate. And well, that acetoheptulose 7-phosphate was what we looked at before when we were looking at that first aldolase reaction. Or, I mean, there is one aldolase reaction and then there's 2 ketolase reactions. Yeah, so don't worry about these details. Please, please, please don't worry about like trying to scramble. This is just going to scramble your brain. We'll do an exercise in class where we'll use some Legos and actually move things around so you can see get a sense of what's happening. But the bottom line, we have these carbon scrambling phase. On net, it can take 6 5-carbon sugars and make 5 6-carbon sugars. Glucose 6-phosphate, which can enter glycolysis or go back through the PPP. And remember, you don't need to go and make this all like put them all into glucose 6-phosphate. You just kind of have to do that in order to scramble them the way to make it all math-wise even out. But we have those 2 points in which we can enter the fructose 6-phosphate or the glyceraldehyde 3-phosphate. And then we can funnel the products into glycolysis from the PPP or into the PPP from glycolysis. Just a quick note is that similar reactions are used kind of like in reverse in plants in the Calvin cycle. And so in this like magenta, these are like glycolysis reactions that we are familiar with. Now we have these pentose phosphate reactions, and then there are some that are specific to the Calvin cycle. Depending on time, we'll talk a bit about plant metabolism at the end of the semester. But the Calvin cycle is very similar. It uses these kind of the same, these transketolase. These are also enzymes from the pentose phosphate pathway. So now let's talk about regulation. So when it comes to regulating the pathway, well, you're going to want to regulate the pathway based on what you need. Do you need NADPH or do you need ribonucleotides? So if you need NADPH, but you don't need ribonucleotides, well, then what you can do is basically you can just run the oxidative phase and take this ribulose 5-phosphate and convert it, do that like 5 carbons into 6 carbons, basically combine those into give you this these products that you can then take back through the pathway. If, however, that would let you keep making NADPH, but you wouldn't be making this ribose. You wouldn't be making your like nucleotides because you're using that ribose to regenerate this glucose 6-phosphate that you can then take back through the pathway. But if you really need NADPH, then you can do that. And how do you know if you really need NADPH? Well, one way is if you have a bunch of NADP+. So NADP+ can stimulate this G6PD. Another way you might, basically though, if you go too far, if you have a bunch of NADPH, now you want to shut this off. You want to shut off the oxidative phase. NADPH is going to inhibit this G6PD. So NADPH inhibits glucose 6-phosphate dehydrogenase. This way, if you have this feedback inhibition, if you have a bunch of NADPH, you're not going to want to do the oxidative phase. And if you're not doing the oxidative phase, that glucose 6-phosphate is now going to become fructose 6-phosphate. Now what? Well, say you want energy. If you want energy, you're just going to want to go straight through glycolysis, take that fructose 6-phosphate to pyruvate, take the pyruvate further, get all that energy. However, if you, instead of wanting energy, you want nucleotides, now you can take that fructose 6-phosphate and you can combine it with these other products. So you can combine it either with glyceraldehyde 3, react with the glyceraldehyde 3-phosphate that we had from a glycolysis, or from products that we got from the Pentose Phosphate Pathway. Basically, we can merge these together, go back and forth between these two pathways in order to generate these riboses. And if we need cofactors, DNA, RNA, whatever. Like basically we can take carbons from here and we can take carbons from here and we can combine these carbons from here and these carbons from here. We can merge them together and we can get our nucleotides. And we could do that even if we didn't do the oxidative phase. We could take these products from glycolysis and make these nucleotides. What if we want both? Well, now we can do the oxidative phase. We could take some of it. We can do the oxidative phase some. We can do this phase some. We can take some out of glycolysis. We can take some out of the pentose phosphate pathway. Basically, we can modulate the activity depending on what we need. But if we really, really just need NADPH, well, here we're just going to do the oxidative phase, use these carbons. So do this like 5 times. So, and then use, or do this like 6 times. In the 6 times, we'd lose 6 carbons. So now we're left with 6 5-carbons, which we could then combine to give us 5 6 carbons. And we could keep doing this, keep doing this, keep doing this. And we'd be able to like just oxidize all those original carbons away, and generate a bunch of NADPH. But if we want to actually use the nucleotides, then that's not going to work unless we funnel more products in from glycolysis. And if we funnel the products in from glycolysis, then we can't get the energy. So you just kind of have to think about various scenarios and when your cells would want to do what. So if you need more NADPH than ribose, run the oxidative and use the non-oxidative to regenerate the G6P to rerun the oxidative. And you can also use the glycolytic intermediates if you really need a lot of NADPH. You can funnel more into the oxidative pathway from glycolysis itself. If you need ribose more than you need NADPH, well, now you can run the non-oxidative with intermediates from glycolysis. So you can, if you want like NADPH and the ribose, then you just go straight through. You go from the top from your glucose to the oxidative pathway, through the non-oxidative pathway, take the ribose and use it. If you just want the nucleotides, then and you want more energy rather than more NADPH, well, now you can just go from glycolysis directly into the pentose phosphate pathway and make things that way. And that way you're not losing that extra CO2. So you still have an additional carbon. You have more opportunity to oxidize. So NADPH is going to be one of the main ways that we regulate the pathway. There is also reactive oxygen species can directly regulate the pathway by inhibiting GAPDH. So remember, GAPDH are from glycolysis, this enzyme. If we take this glyceraldehyde 3-phosphate that we get from the pentose phosphate pathway, say, here we can, if we took it and used glyceraldehyde 3-phosphate dehydrogenase, that would give us our 1,3-phosphoglycerate. And then the next step, and then that's going to kind of like be driven into glycolysis. If we inhibit this step, now this glyceraldehyde 3-phosphate, even that one stuff we get from glycolysis, is going to be driven towards the pentose phosphate pathway and used to make our like nucleotides. So by having the reactive oxygen species kind of directly oxidize and inhibit this enzyme, you're able to drive things towards this, towards the non-oxidative phase of the pentose phosphate pathway and the production of these nucleotides. So multiple levels of regulation. And again, it gets kind of complicated. So let's go back and think about kind of the key points. And then we'll talk about the G6PD deficiency a little more. So the key things about the pentose phosphate pathway. It's also called the hexose monophosphate or HMP shunt, because you have this 6-carbon, this 6 monophosphate sugar, this glucose 6-phosphate, it's getting shunted to the pentose phosphate pathway rather than going into glycolysis or into glycogenesis. It happens in 2 phases, an oxidative phase and a non-oxidative phase. In the oxidative phase, you generate 2 NADPH and you lose a carbon as CO2. So you're going from a 6-carbon sugar to a 5-carbon sugar, this ribose 5-phosphate. The NADPH is the main thing we get out of there, and it's needed to combat oxidative stress. It's used to regenerate antioxidants like glutathione, and it's also used for the synthesis of lipids, the making of steroids, various anabolic reactions where we need that NADPH. After that, we enter the non-oxidative phase. The non-oxidative phase, here our reactions are reversible, and we have carbon scrambling using transaldolase and transketolase. This is going to basically produce our ribose 5-phosphate, which can be used to make nucleotides and some enzyme cofactors. It's also needed for, so that's needed for rapidly growing cells. And if you don't want to go all the way to ribose 5-phosphate, you can produce glycolytic intermediates that can feed into glycolysis for energy or feed back into the PPP. And the net result of all this scrambling is that you can convert 6 5-carbon molecules into 5 6-carbon ones. And so, but that was starting from 6. That would be starting from 6 carbon ones, because then you're losing 5 from each. If you went through this 6 times, you'd lose 6 CO2. And that would leave you with 6 of your 5-carbon sugars that you can interconvert through those transaldolase and transketolase steps in order to get 5 G6Ps. If you were to take those back through the oxidative, if you were just to keep doing the oxidative phase, you'd be generating NADPH and oxidizing these all the way down, well, the equivalence of it all the way down, without generating any A2P though. So if you want ATP, you want to go the glycolysis route. Depending on the cell's need, they can alter how much they use, which pathway and which phase of the pathway, because you can convert, take products from glycolysis into this non-oxidative phase, and you can take products from this oxidative phase into glycolysis directly without having to go through the oxidative phase. But if you want NADPH, you need to go the oxidative phase. In this oxidative phase, the kind of rate determining step is going to be this glucose 6-phosphate dehydrogenase, this G6PD, or this G6PDH. And so let's talk a little bit more about that. So remember that G6PD, this glucose 6-phosphate dehydrogenase, is needed to regenerate our antioxidants. How it does this is by generating NADPH, and that NADPH is then going to be used to regenerate our used up antioxidant, so like our used up glutathione. So glutathione was taking the hit from the reactive oxygen species so that our proteins and our nucleic acids and things like that didn't have to. As a result, what's going to happen is you're going to oxidize the antioxidants so that they're no longer antioxidants. In order to make them antioxidants, we use NADPH. In order to make NADPH, we use G6PD. If we have a problem with G6PD, we can't make NADPH. And not only can we not make that first NADPH, well, that was our pathway step to getting the second NADPH down the line. And so what's going to happen is that we're going to build up this NADP plus, which is going to further inhibit G6PD, and we're not going to have the G6PDH that we need. In our red blood cells, because they have so much oxygen and they don't have those other kind of compensatory mechanisms, this oxidative stress is going to build up and it's going to damage them. In infants with bad G6PD, this can actually cause like jaundice because, well, the red blood cells are breaking down, one of the things in them is going to be heme from holding on to all that oxygen. The process of kind of breaking down the heme actually needs NADPH. And additionally, like you're going to have a lot more breakdown when these cells are damaged. And so babies can actually get problems. Like one of the ways that G6PD deficiency is realized in infants sometimes is because they're more likely to have this neonatal jaundice. And so, yeah, and if you're wondering about like why jaundice is treated with light, basically it converts bilirubin, so one of the breakdown products of your heme, into a form that's soluble and can be like excreted out in the urine without requiring the liver to process it. That's in babies, but what about in adults or any person? Basically, there are different ways in which you can think about, like if there's more oxidative stress in the cells and the person's cells can't keep up, then you're going to have issues. And one of the main issues that you recognize is going to be like hemolytic anemia. So basically, the red blood cells are going to get destroyed because of the oxidative stress that can't be counterbalanced. Some drugs like chloroquine and hydroxychloroquine, they actually like kill parasites by inducing a lot of oxidative stress. And sorts of other sorts of chemicals can trigger this, like favabeans. Basically, if you have more oxidative stress happening in the cells, yeah, like it's gonna kill the parasites, but it can also, if your cells can't keep up, then it's going to cause issues. And so when you have these drugs that cause more oxidative stress in the cells, and you have a G6PD deficiency, this can cause like a crisis where the blood, where if people like eat these fava beans or take these medications, they can get this hemolytic anemia triggered. So this is an X-linked disorder, which means that it's on the X chromosome. Biological females have 2 X chromosomes mostly, and so biological males have 1 X chromosome and 1 Y. And so a male, if they have 1 bad X chromosome, then they can like have the disease, but a female, they would have like 2 X chromosomes, so they had like 2 chances for it to be okay. And so they would be like probably not affected. I say probably because the way that there's like this thing called genetic mosaicity. And so basically 1 version of each of your chromosomes is inactivated in each cell so that you don't have too much X chromosome activity. And depending on which one gets inactivated, some of the cells could have the functioning version and some could have the non-functioning version. But typically they wouldn't show any symptoms. But in a male, they only have 1 X chromosome, and so they're more likely to show the symptoms. In terms of why this might be maintained if it causes these issues, well, it doesn't usually cause these issues. It doesn't often happen. It has to have like one of those triggers. And what they think is that like some parasites, like malaria parasites, the reactive oxygen species that's kind of building up in the cells of people with a G6PD deficiency, just like normally, what's going to happen is that's actually going to kill the parasites, just like those drugs induce the killing of the parasites. These people's cells are kind of like already doing it. And so that can provide an advantage in places where there are high prevalence of things like malaria. As a result, we see that the prevalence of G6PD deficiency in the United States is highest in Black males. So the U.S. Department of Defense found that a full 11.2% of non-Hispanic black male soldiers have the condition. However, it's not like routinely screened for. And so I feel like it should be screened for, but it's not screened for. You can say, well, maybe because it doesn't cause problems most of the time, maybe it would like overly worry people. But I think it's good to know whether you have a G6PD deficiency or not, especially if you're in like a higher risk group, especially before you go and you take some medication. But that's just my thinking, and that is your medical connection to the pentose phosphate pathway, because remember that G6PD was our step into the pentose phosphate pathway, the step that the kind of like committed step, that rate determining step, that irreversible first step where we generate the NADPH that we need to combat the reactive oxygen species and generate the fatty acids and our steroids. That's the oxidative stage is the easy part. And then you just have that carbon scrambling, which you don't worry about trying to get your brain around. Just know that we have those two kind of places we can enter and leave glycolysis and feed into and out of the pathway through this fructose 6 phosphate and our glyceraldehyde 3 phosphate. And know that depending on what the cell needs, we can regulate how much of which pathway we want to go through. Hopefully the exercises in class will help clear some of this up. And we can focus more on just like thinking about what would happen in various scenarios. Sorry if I scrambled your brain there, but my brain's a little scrambled too.